Swayam Prabha. Digital India. Educated India.
Good morning to all of you. So today we are starting our discussion on op-amp or operational amplifier. Operational amplifier or op-amp. Operational amplifier. Fine. So we already know what is an amplifier, right? So amplifier is a circuit which can amplify an input signal. That means for an amplifier, if you give one signal at its input, at its output you can expect and the amplified version of that input signal, isn't it? Then why it is called this operational, this op-amp? That is because in earlier days, means during the days of this analog computers, this op-amp used to be used for doing different mathematical operations, okay, for solving this differential and integral equations. So that is why it is called, as it was being used at that time to do some different mathematical operations. So its name this operational. So I hope this is clear to you, right? Why it is called this operational amplifier. And we have already seen from our previous discussion on bipolar junction transistor as well as on the MOSFET amplifier, we have seen that definitely one transistor is required, at least one transistor is required to make one amplifier, right? So this op-amp also, this consists of transistors, right? And generally there are, in op-amps there are 20 to 30 transistors. Okay, a op-amp consists of 20 to 30 transistors. Okay, so then obviously these 20 to 30 transistors along with the other passive component, for example resistors, they are fabricated on a same silicon chip and they are integrated with each other, right? So this op-amp is also an integrated circuit, right? Right, because all the components, including the active component, which consists of this active component as well as the passive components, they are fabricated on the same silicon chip, right? So op-amp is also an integrated circuit. You understood my point? Okay, so this op-amp as a circuit is not a very new circuit, but in late 1960s people used to use these op-amps, okay, and one of the quite popular op-amp is IC number 741. Okay, in your laboratory course also you will be using this IC 741, right? And to be very specific, quite specific, you can think of the name as this mu A 741. This stands for the company name, which is actually the Fairchild. Right. This Fairchild, this is the company which has fabricated this, and this is the 741, which is the number of this IC. And in this IC, generally 20 to 30 transistors are actually there, right? And this 741 IC is quite popular. This is very popular. Still, this is being used in today for implementing different circuit still today. Now if we say like this is 20 to 30 transistors, then these transistors can be either a BJT or a MOSFET. So for making these op-amps or this operational amplifier, you can use this bipolar junction transistor or this MOSFET. Fine. So you can use either the total circuit is made up of BJT, or the total this op amp is made up of this metal oxide semiconductor field effect transistor. Okay. Let us now in the next page quickly see the circuit symbol of this op amp. Each op amp has two inputs and one output, and generally in circuit it has been represented like this. This is one input, this is the second input, and this is the output. So let us write that this is the input, this is the output, and these are the inputs. Right. For one of the input, beside this input line, we place one negative sign, and for the other one, we place this positive sign. Okay. The negative terminal, or the terminal beside which we have denoted this negative sign, okay, it is termed as inverting terminal. And for the other one beside which we have written this positive sign, it is called as non-inverting terminal. Fine? Right. So, besides, from our previous discussion, we also know that for any amplifier, proper biasing has to be there, right? Without proper biasing, one amplifier cannot work. So, for operational amplifier as well, we should have the proper biasing. So, for this operational amplifier, generally two type of supply voltages are being used. One is called this V plus supply, or the positive supply positive supply source, and the other one is V negative supply. So this is the negative supply voltage. And if you recall our discussion on this bipolar junction transistor amplifier as well as the MOSFET amplifier, so there also we have seen this type of biasing, right? One positive voltage biasing at the top, and at the bottom the negative voltage biasing, isn't it? Right. So here this inverting terminal, from this name itself it is quite clear that if you give here any signal, obviously after proper biasing and proper biasing of all this V plus, V negative, and you know, this from output to input connections, we will discuss more about this in our later discussions, right? But if after proper biasing, if we apply, suppose this terminal is grounded, this positive terminal or the non-inverting terminal is grounded, and if you apply any signal here at this inverting terminal, then at the output what you can expect is the amplified version of this input, but there will be an 180-degree shift compared to the input signal. That means, just for very simplicity, if I say, like, suppose you have a input signal here like this, okay, at this inverting terminal, okay, and when this terminal is grounded, okay, and obviously there are some other things, like there should be some feedback from output to input, okay, that we are not discussing here, but yeah, you know, in today's class only we will see that we have to properly bias this, and the circuit has to be connected properly. Then if we apply here some signal, some sinusoidal signal, then at this output what we can expect is that this will be obviously amplified, but it will be obviously amplified. So you can see the magnitude of this, you know, amplitude of this is less compared to the magnitude of this output signal. So obviously amplification has been done. And at the same time, you can also notice that there is an 180-degree phase shift between this input and this output, right? So it means that the input signal is actually inverted. Fine. Similarly, on the other way, you can think of, right, obviously after proper biasing, if you now ground this, okay, and apply the signal here, okay, at this input terminal, right, and suppose in a similar way the input signal is here like this, then at this output what you can expect is again the amplified version of this input, but the signal will be in the same phase of that of this input signal. So there is no phase difference between this input and this output, right? And this is only happen when you apply the signal at this non-inverting terminal. So is that clear to you? Okay. Another important point is here that this op amp, as you can see, as they are using this plus supply and as well as this negative supply voltage, both positive and negative supply voltages. So this op amp is a direct coupled device. You can consider the overall total this op amp as a single device because internally there are 20 to 30 transistors, but you can consider the total thing as in one unit and one device. So that way you can think this for op amp as we are supplying both positive and negative supply voltage. So this op amp is a direct coupled device. These op amps are generally direct coupled device, right? So what does this direct coupled device mean? That means this op amp can amplify this AC signal, right? At the same time, if you use some DC signal, this op amp will also be able to amplify that DC signal. Okay, and when you are applying this AC signal, no need to use any coupling capacitors. Fine. So I think then the circuit symbol of this op amp is clear to you. Isn't it? So just to recap, for op amp we have two input terminals. One input terminal is called the inverting terminal or inverting input terminal. Beside that inverting input terminal, we have to write this negative sign symbol, right? And the other input terminal is this non-inverting input terminal, beside which we will write this plus sign, right? And it has one output. This is the output, and for proper biasing of these inside transistors, we use this V plus supply as well as this V negative supply, both positive and negative voltages, right? And also we have discussed about this op amp is a direct coupled device, so that means this op amp can be used for amplifying an AC signal. At the same time, op amp can also be used for amplifying and DC signal. Means it can also work. This op amp can also work uh, in DC. Means we will see that, okay, in our next in today's we will discuss about couple of examples where we see that we apply some DC bias at one of these terminal, either this inverting or at this non-inverting terminal, and we will see what will be the expected output from this op amp circuit. Fine. So in the next page, let us discuss about what are the characteristics of an ideal op amp, right? Because until and unless we know the characteristics of an op amp, we cannot use this op amp in a circuit, right? So let us do that in the next page. So ideal op amp characteristics. So before we discuss this each point one by one, let us first draw the equivalent circuit of an ideal op amp. So op-amp ideal equivalent circuit is, let us draw it. It will take some space. So let us draw it in a bigger way. So you know there are two inputs and one output, right? So these are these two inputs and this is this output, right? And one of the input is negative. We have to write negative, that is the that is the inverting terminal of the op amp, and the other one is positive, which is the non-inverting terminal of this op amp, and this is the output. So here the voltage would be the output voltage V naught, right? And this, let us say that this is terminal 1 and this is terminal 2, and the applied voltage at terminal 1 is V1 and the applied voltage at terminal 2 is V2. Then this, we have discussed that this op amp is nothing but an voltage amplifier, right? So that way you can think of this, the output is dependent, okay, on this, or maybe better, this is a dependent source, so we should use this symbol, this plus minus, okay, and the value of this, or the amplitude of this dependent source is A of OD into the difference between these two input voltages, that is V2 minus V1, right? And so this is the output. So from this discussion, what you can see is that, or let me write this plus minus here, that this V output is nothing but equal to the gain of this op amp into the difference between the difference in potential between the two input terminals. And see how are we taking this difference? It is V2 minus V1. That means the non-inverting terminal voltage minus the inverting terminal voltage, right? And as you can see inside, we have just shown it up to this, right? So that means nothing is there between terminal 1 and terminal 2. So you can consider it is an open circuit. So that way you can consider the input resistance between terminal 1 and terminal 2, that is between non-inverting and inverting terminal, is actually infinite, right? So let us write that first here. So this ideal op amp has input infinite resistance. So input resistance is infinite. Fine. This is one that we have understood. Okay. So if the input impedance are infinite, and then if you are connecting one voltage source here V1, then can any current flow inside to this op amp? No, right? Similarly, there will be no current, okay, flowing from this V2, okay, to this op amp. So that means input currents to the op amp is 0, right? That you understood, because the input impedance is infinite, right? What about the output impedance? Can you comment on it? See, this output for this ideal op amp, you can see from the circuit symbol, from this equivalent circuit diagram, that this output is connected with this dependent voltage source, and then it is grounded. So voltage source impedance is 0. So that way output is connected with this ground only. That means the output resistance of this ideal op amp is 0. So let us also write that part here. Output resistance is 0, right? Okay. Then what is the output? We have already discussed some time back. This output, or this output voltage for this configuration, if the voltage is applied here is V2 and the voltage applied here is V1, then the output is nothing but AOD into V2 minus V1, right? Here this AOD term is called the differential voltage gain. This AOD is called differential voltage gain. And for ideal op-amp, this differential voltage gain is actually infinite. Okay, that means if you have some here, some V1 here, some voltage here, and if we apply some voltage V2, then this output voltage, okay, from this is expected to be infinite, right? It's a very large value. But is it really possible? Think about it. Because we are supplying the voltage that is plus V supply, and here this V negative supply, right? So if the output is positive, then you can obviously guess the output can maximum go till this V plus supply. If this output is negative, then maximum this output voltage can be this V negative supply. But important thing to remember is that this gain or the differential voltage gain of this ideal op-amp is infinite, right? So let us write that part as well. So differential open loop gain is infinite. Now remember here, this is open loop gain. So that means when we don't have any connection between inputs and the output, that means there is no feedback. When we have a feedback from this output to the inputs, right, then this then obviously the differential gain will be there, but then the output gain means compared to the input, whatever you are getting at this output, okay, you cannot say that directly to that. Suppose the output is some positive, then you cannot say the output is V plus supply. Okay, it depends on the gain of this amplifier, op-amp amplifier circuit. Then at that gain is called the closed loop gain or gain with feedback. Okay, but if you have to use only this op-amp in this configuration, right, then you can think that this op-amp has a differential open loop gain which is infinite, right? Then see, one more thing can also happen here, like V output voltage. Here you can see it is nothing but AOD, that is differential voltage gain, which is actually very large, right, very high. For ideal it is infinite, into V2 minus V1. Now what will happen? Think, if this V1 is equal to V2, that means same signal, that the common signal is being applied between terminal 1 and terminal 2, then what is the output voltage? Right, exactly. Then it is, you can see the output voltage should become 0, isn't it? So this V output is expected to be 0 from there. So this is another important property of this ideal op-amp, that is the common mode gain is 0. Okay, so that means if you apply the same signal between this terminal 1 and terminal 2, okay, and if the signals are same, then the output voltage is 0. So that way you can also think that this op-amp has the capability to reject the applied common mode signal, right? So this property also called this common mode rejection. Fine. Okay. And one more thing, as we have discussed in our last page, that you can also apply some AC signal here at this V1 or at this as a V2, right? Along with this DC, right? You can apply DC or you can apply also AC. Then for AC, you have a term of this frequency, right? Then when this frequency term is coming at this input signal, then obviously there is also another parameter that we have to consider, that is called the bandwidth, right? What is the range of frequencies that this op-amp can handle? Means I can fruitfully get the output, because we have already covered the filter part, so you know what is bandwidth, right? So that way, for ideal op amp, the bandwidth is also infinite. Fine. So I hope from this point it is clear to you uh, what should be the characteristics of this ideal op amp, right? So all these properties are quite important in terms of analyzing and designing in a circuit using op amp. Fine. Okay. So if this part is clear to you, then let us also discuss in the next page uh, what are the characteristics of an practical op amp, okay, or how the performance of a practical op amp differs from this ideal op amp characteristics. Fine. So practical op amps. So let us first also draw the equivalent circuit of an practical op amp, right, which looks something like this. Then inside, similar to our earlier case, we have this inverting terminal, we have this non-inverting terminal, right? But and this is the output terminal, right? This is V output or V naught that we have indicated in the last last page only, right? And this is these two terminal input terminals, terminal 1, terminal 2. Here the voltage applied was V1, here the voltage applied was V2, right? And for ideal op amp, we have seen the resistance between this terminal 1 and terminal 2 is actually infinity, right? So that way no current is actually flowing inside this op amp from any one of this terminal, flowing in or out, right? But for practical op amp, this is not actually infinite, the input resistance, but it has an finite value, but this value is very high. Okay, this R input is very high. So number one is R input is very high, but it's not actually open circuit. Okay. The other thing is that in the last page we have seen that here we have a voltage source only, right? This is plus, this is minus, right? And this voltage source magnitude we have represented AOD into V2 minus V1, right? And this was directly connected with the output because there was no output resistance for ideal op amp. But for practical op amp, we do have an output resistance here. So we say it as, suppose indicate it as by R naught, right? Then if you look from this output side, then you have a finite value of output resistance, or we can write our output is finite but low. Okay, this output is not very high value, it's low only, small resistance, but it is a finite value. It is not zero at what we have considered for an ideal op amp. Fine. Okay. One more thing is that in earlier page or in previous page we have considered this AOD, or this differential open loop differential gain of this op amp is infinite. But again, this AOD also not infinite for practical op amp, but AOD is generally very high. So AOD is very high. Okay, so if I say like high, very high means it may be this 1 lakh or more. Okay, so the gain is very high. Okay, but it is not infinite or more, right? So here you can clearly see then that this practical op amp deviates a lot, okay, compared to the ideal op amp, right? However, for our circuit analysis and design purpose, for this course we'll consider the op amp to be as an ideal one. Okay, using that ideal op amp characteristics only, we will proceed and design and as well as analyze a circuit which is using one or more op amps. Fine. Okay, so here if I ask you, we have drawn previously, you remember this voltage transfer characteristics, which is nothing but a plot between the output voltage and this input voltage, right? So if I ask you to draw the same plot for this op amp, this practical op amp, how does it look like? Can you guess? So what are we doing here is plotting the output versus input voltage characteristics. So here we have this V output and here we have this V input, and this is the zero voltage, right? For input voltage as well as for the output voltage. So zero means, op amp, this output voltage depends on the difference between these two input voltages, right? The difference. Right. So that way this input voltage is nothing but the difference voltage, right, between these two input terminals, which is V2 minus V1. So when this V2 minus V1 is positive, right, and if this op amp is operating in the open loop condition, then what do you expect for when this V2 minus V1 is positive? Last page only we have discussed, when this V2 minus V1 is positive, then that means this is at higher value compared to this V1, right? So this is non-inverting terminal. So the output is expected to be positive. So positive what voltage? The voltage for this op amp, if the positive maximum supply voltage is this one, V plus supply, right? Then here also, and if you suppose indicate that thing here, means this voltage here, which is this V plus supply here, right? Then for this V2 minus V1, the output will also be close to that, right? Please remember one thing, that we are using the term it is close to. So it will be this close to this supply voltage, right? But still you can see there will be some difference between this supply voltage and this output. If let us say that this is delta V, okay, right? So what will happen if this V2 minus V1 is negative, that is for this side, left side? So here you can see the voltage applied at this terminal 1 is higher than this terminal 2, right? So obviously then the output V out will be some negative voltage, and as it is operating in the open loop condition, the negative voltage will be the voltage will be trying to flow, achieve the voltage of this maximum of this supply negative voltage, right? So here if we indicate similarly this voltage as this V negative supply, right, then the output voltage will also try to approach to this value, right? Again you can see here there will be some difference delta V between this V negative supply and this output voltage, right? Okay, now tell me one more thing. What is this? If we take a slope, okay, between this between this V output and this input voltage, this is basically now the V input, right? V2 minus V1 is nothing but here this V input. If you want to write, if I have to write it, I can write it here. This is V input. So this V output versus V input plot, the slope determines the gain of this amplifier, isn't it? We have done this thing a couple of times, right, previously. So for ideal op amp, think about it, for ideal op amp the output voltage characteristics would be, it will come like this and then it will be in a straight line, right, and it will be in this because it is infinite, right? The slope is, right, then the slope will be, this angle will be 90 degree. But for practical op amp, as you can see, this is high but it's not infinite, so we have an finite we have an this angle will not be 90 degree but it will be close to 90 degree but not equal to 90 degree, right? It will be less than it. So we have a slope here and here also we'll have a slope, right? So this slope is nothing but this A of OD. Is this part clear to you? Okay. Now here two important things, that what is the value of this delta V? Okay. This delta V values will be in the range of 1 to 2 volt for old op amps. Old op amps means earlier technologies op amp, okay. And this delta V will be very small, like maybe in terms of 10 or 20 millivolt, okay, in modern op amps. Fine. So you can see here from here that for modern op amps this output voltage is very close to that of this two supply voltages, either it is positive supply or in case of for this negative supply. Is this fine? Okay. Now here one more point. Suppose this output of this op amp is driving another op amp or maybe driving some other circuit. So for another op amp also, if it is driving another op amp, then we also have an output load, right, here, isn't it, which is nothing but this RL. So this is this V out, right? Fine. Now think about it, when this V output, okay, is a positive value, this output voltage is a positive voltage, then what will happen? Then this op amp will act as an supply, right, for current. Then obviously this is positive, this is RL, so depending on the value of this RL and this output voltage, one current will flow. So this op amp will act as a supply for this current, right? Similarly for the other case, right, suppose if you consider this V output now negative, then in that case, depending on the value of RL and V out, one current will flow, right? This is the current that will flow. So in that case, this op amp output will act as a sink, right? So for whether it is a positive voltage or negative voltage, see, this op amp either has to supply one current or have to take another current, means act as a sink, isn't it? So for both cases, the current will be flowing either in or out of this op amp output terminal, right? Right. Then, is there any limitation of this current or this maximum value of this current? Yes, there is a limitation. So, while you are designing the circuit, please remember this maximum current. Okay, this output from this, which can be supplied by this output terminal of op amp or can be synced by this op amp is the maximum value is around in the range of 20 milliamps, okay, for practical op amps. Fine. So while designing the circuit, you have to ensure that the current value you are taking to this load or the amount of current that is being supplied to this output terminal of this op amp should not exceed this 20 milliamps current rating, right? So you need to take a look into this part. Fine. Okay. Then if you have understood this part, then another very interesting thing is that, notice here, see this, for even for either it is practical, so the point that we are going to discuss now, that is valid for this practical op amp as well as for an ideal op amp, for both. Okay. That is, this AOD or this open loop differential gain for any op amp is very high. See, this weight is 1 lakh or more. This is very high, right? But what is the output voltage maximum? Maximum output voltage, whether it is positive or negative, it depends on these two supply voltages, and the values of these two supply voltages are finite. So that way the output is V output is also finite, right? So if this V output is finite, right, then you think about this equation, that V output is equal to A of OD into V2 minus V1, right? Or that way this V2 minus V1 equal to V output by V of OD. Now this V of OD is very large number, this, right? This is a very large number, whereas this V output, it is governed by the supply voltage, which may be 5 volt or 10 volt, right? Maybe even smaller than that, and this is maybe 1 lakh or even more. So that way what you can see is that V2 minus V1 is quite close to 0, or that means V1 is equal to actually V2. So that means for this op amp, okay, the potential between the potential here, that is at V1, and the potential here V2, op amp will try to arrange these two potential such that, okay, in a closed loop operation, okay, in a closed loop operation, this V1 potential will be close to that of this V2. Fine. You understood my point? So that means you can assume that for closed loop operation, the potential applied at this input terminal, means one of the input terminal, is nearly equal to the potential to the other terminal, right? So this is the concept that we are going to use quite frequently for our next op amp circuits. Okay. So let us now do one basic circuit using this operational amplifier, okay, where the signal, okay, or maybe it's a AC signal or maybe a DC supply voltage that is being applied to this negative, okay, to this negative or the inverting terminal. Fine. So let us do that in the next page. So here Let us also first draw the circuit, then we will discuss. So in the circuit, we have one op amp like this, right? This is the inverting terminal, this is the non-inverting terminal, and we are applying the signal or maybe a DC voltage, anything, okay, here in this inverting terminal, and we are representing it as this Vi or V input, okay, and the non-inverting terminal for this op amp is grounded, fine, right, and this is the output, so this is V out, right, and here we are not showing explicitly the supply voltages. Here you should know it is V supply, okay, let me write it here as well, but it is not compulsory for all cases to write this to supply voltages, okay, or to show the supply voltages. Now this op amp, we are not operating in this open loop condition, but rather we'll try to operate this op amp in a closed loop condition. So in a closed loop condition means we have a feedback taking from this output and we are connecting that feedback here, and that feedback element is a simple resistor. Got my point? That means whatever is the output voltage, some part will also go to here to this input part of this input and is connected with the inverting terminal, right? And let us say the value of this resistance is R1, the value of this resistance is R2. Fine? Okay. So now tell me how to start start the analysis, okay, for this circuit. So what we are interested, we have to find what is the gain for this total circuit, what is the input resistance, okay, input resistance, these three stuff, right? Then how should we approach? Let us say that let us take 2 points here, like say this node is this point is point to this 1 and this point is point 2. So 2 is already been grounded, right? But do we know what is the potential at this point 1? I think we know. Why? Because in the last page only we have discussed the potential at this terminal. If we are saying that suppose it is V1, right, then and the potential here if we are saying this V2, right, then as this gain, okay, as this gain is very large, right, then we have just now discussed, then the V1 will be equal to V2, right, then here V2 is already been grounded, right, then this V or the potential at this node 1 will also become 0, right. So you see that this is grounded, right, but here due to this feedback and due to the very high gain, okay, of this op amp, okay, this is basically the open loop gain, so let us write that as well here. So this is this open loop gain, right? This open loop gain is very large, and that is the reason we can write this one, right? If we can write this, then the potential because this node 1 is becoming 0 volt, right? That means you can also consider the node 1 is grounded, right, because it has 0 potential. But the thing is that, is it really grounded? Can any current flow from this node 1 to ground? The answer is no. So it is at ground potential. Potential is at ground, right? But it is not directly connected with the ground, as no current can flow from here to here. No connection, right? So this ground is called the virtual ground. So you understand what do you mean by this virtual ground and why this virtual ground is happening here? Okay. So if so, then tell me, what is the current that is flowing from this Vi to this here? What is the current flowing through this? Tell me. What is the current? See, this potential V1 is 0. So this current is Vi, nothing but R1, right? Can any current go to inside op amp? No, right? Then the same current, this current only has to flow through this R2, right? Then what will be the potential of this V output? Then V output will, you can directly write it as V output equal to minus of this current. If we say like this current is at this I1, then it is I1 into R2, right? So which is nothing but, if we just substitute it here, it is R2 by R1, right? Okay, now I can also write it like this, V output by V input. So what is this V output by V input? Equal to minus R2 by R1, and say suppose this R2 is equal to 4 times of R1, then this V output by V input is equal to minus 4. What is this V output by V input? Is the output voltage by input voltage. This is nothing but the gain. So gain, but this is the closed loop gain, because now we have a negative feedback. So you see the closed loop gain is finite, it is not infinite, right? And what is this closed loop gain? The closed loop gain, actually this minus 4 we are getting from this, right? So let us like in general, for this type of circuit it is minus R2 by R1, right? So that means compared to this output voltage, compared to this input voltage, the output is amplified by 4 times. So amplification is happening. So then definitely this is again one amplifier circuit, and as the signal is being applied, it may be signal or it may be DC voltage, right? Anything is fine, right? As this has been applied here at this inverting terminal, so this type of amplifier is called the inverting amplifier. Inverting amplifier. So is it clear why it is called inverting amplifier? Because the signal or the DC voltage is being applied at this. And why it is amplifier? Because definitely you can see this output voltage is being amplified depending on the value of this, obviously R2 and R1, right? And you have also noticed, as is the inverting amplifier, you can see the gain is negative, right? This negative sign. So that means if you give here plus 1 volt, then for this configuration, if this R2 by R1 equal to 4, then here if it is plus 1, then it will become minus 4 volt. Plus 1 volt DC, then minus 4 volt DC. If it is a sinusoidal signal of 1 volt, then here it will be a sinusoidal signal of 4 volt, right? If it is a 1 volt, then it becomes 4 volt, but there will be a 180-degree phase shift, or the signal will be inverted. That's why it is called the inverting amplifier. So is it clear to you? Okay. And one more important thing here to notice is that, see, this here gain, this is independent of, this gain is this independent of this op amp gain, right? Because here this AOD term is not coming, right? It is completely dependent on the this components which are connected with the op amps. So that way, if an op amp is being used in a closed loop condition, we can control the gain of this op amp, I mean the overall closed loop gain of the circuit, quite precisely, right? Because if you are using in an open loop condition, right, then that op amp gain can vary a lot, because depending on the manufacturing, it is very difficult to control that gain exactly, right? But now we are using the property of very high gain of this op amp, but ultimately for the closed loop circuit, we can see that the gain is independent of the op amp's closed loop gain. Is that clear? Fine. Now let us discuss about the input resistance. So what will be the input resistance? Input resistance if you look from this side, right? So this is R in. So see here, if you look from this side, this is a virtually grounded, right? So you can think of this as a zero potential. So that way R in is nothing but the resistance, this R1. What my point? Okay, because you can also think from here. See, the current here is I1 and the voltage here, is, this is Vi, this is 0, right? So you can think from this current voltage equation. That way also you can find the, R in would be this R1 only. Okay, so here from also you can notice that this R in is only this R1, okay, which is the external resistor. It is not dependent on the on this op amp, right? So I hope that way this inverting amplifier part is clear to you, how to analyze, right? So I think today not much time is here, so let us stop here today. We'll discuss in tomorrow's class.